Our 6-5 notes are about a difficult but yet important topic, conditional probability. Conditional probability is the probability determined after an earlier event has already occurred. The notation is as follows. Probability of A given B. This line right here implies the given conditional probability. It means we want to know the probability of the first thing listed given that the second thing listed has already occurred. Let's take a look at a Venn diagram which depicts a conditional probability. Talking about the probability of A given B. Let's first talk about the probability of A. This is what we want to calculate, the probability of A. So in a universal Venn diagram, this is what your diagram would look like. Set A would be this bubble on the left, including the AND. Now, if we're in a conditional state and we already know that B has occurred, this narrows down our view to only the bubble of B. This becomes our new universal set. We don't consider anything outside of this bubble because we already know that B has occurred. Once B has occurred, but we still want A, the only portion that's left that also contains A is the AND. So, a conditional probability can be calculated by the AND divided by the whole given set. And that's where we're going to get our calculation for a conditional probability. The AND over the given set. You can show a similar diagram for B given A. At the bottom of your page, you have various forms of this exact same formula. So, you really only need to memorize one of them. And I like to write it in words myself. I think of a conditional probability as the probability of the AND, both terms combined, divided by the probability of the second term, the given. Now we're going to apply it to various problems. We want to find the requested probability for each problem. In part A, we have the probability of A and we have the probability of A and B. We want the probability of B given A. Since I want a conditional probability, the first thing I'm going to do is write my conditional probability formula. So the probability of B given A. As I had mentioned, when I calculate a conditional probability, I think about the AND over the given, or the AND over the second letter. So, the probability of B given A will be equal to the probability of A and B, the AND, divided by the probability of the second letter, or the given information. In this case, that's going to be A. Now, let's plug in what we know. We don't know the given or conditional probability. We do know the probability of A and B is 0.24. And we do know the probability of A is 0.6, so we fill in those pieces. Now you can see what we want, the probability of B given A, is simply 0.24 divided by 0.6. If you calculate this, you'll get the probability that you desire, which is 0.4. And that's our answer. Part B gives us the probability of B and the probability of B and A, and wants the probability of A given B. So once again, I'm going to go ahead and write the equation for what I want. The probability of A given B will be the AND, so it'll be the probability of A and B once again, and it will be over the probability of the second term. In this case, in this conditional probability, b is our second term, so it belongs in the denominator. We fill in what we know. We do not know the conditional probability, so we leave that as the probability of A given B. We do know the probability of the AND is 0.12, so we can fill in our numerator. And we do know the probability of B is 0.4, so we can fill in our denominator. This will once again let us solve for the probability of A given B pretty directly by just dividing 0.12 divided by 0.4, or 0.3. Part C is a little bit more difficult. It gives us the probability of A and it gives us the probability of B given A, but we want to find the probability of A and B. Since we have a conditional probability, let's go ahead and write the probability statement for B given A. The formula is the AND, so A and B once again on top, divided by the probability of the second term, the probability of A. Now I'm going to fill in what we know. This time I know the left side is 0.27, and I don't know the top, so I'll leave it as the probability of A and B. I do know the probability of A is 0.5, so I can fill that in as well. To solve for what I want, I have to get rid of this division by 0.5. You get rid of division by multiplying by 0.5. So I do that to both sides. The 0.5 cancels on the right, leaving me with the probability of A and B. And on the left-hand side, if I multiply 0.25 by 0.5, I get 0.135. And that's the answer. Now, if you look at the front page, there's another equation that you can solve for the probability of A and B more directly. However, I try to memorize the least amount of formulas as possible. And since essentially that other formula is just the same formula, just manipulated, I just revert back to my basic formula, and then I can use my equation solving skills to get whatever probability that I desire. Let's move on to a bag of marbles. When I calculate the conditional probability of a bag of marbles, I'm going to actually steer away from the formula. While the calculations can be done with the formula, I feel that they're more confusing than they're worth. So let's take a look at example 2. We have a bag of marbles containing 2 orange, 5 green, and 1 pink marble. So that means that we have a total of 8 marbles. Part A wants us to find the probability. Given that a pink was selected but not replaced, what is the probability that the second will be orange? So let's write this probability. Probability that the second is orange, given that the first was pink. Okay, so this is a conditional probability, and we're going to go ahead and calculate it just by essentially taking the first event and thinking about what happens to our set. If a pink marble was taken out and not replaced, think about what happens to the set. The universal set would go down by 1 marble, so now instead of having 8 marbles, we now have 7. And when you take a pink one out, that means there's no pink left. So we have 7 marbles, no more pinks. Now with that new set in mind, now think about the probability of the event we want, of getting an orange. Well, there are only 7 marbles left, and out of those, 2 are orange, so the probability is just 2 out of 7. Now notice, I did not use the formula. Yet again, you could have used the formula, but in my experience, it's just been more complicated for students than it's worth. So our answer is just 2 out of 7, or you could give the decimal or percentage as well. All right, so let's take a look at part B. Given that an orange was selected and replaced, on the second pick, what is the probability of green? Okay, so we want second green, given that the first was orange. Now keep in mind that it is replaced. If I take an orange one out and I put it back in, what happened to the bag of marbles? Well, if you put the marble back in, you're resetting the environment. These are actually independent events. So what that means is that the probability of the second one being green is the exact same thing as the probability of green in the first place. Or in other words, 5 out of 8. Moving on to C. Given that a green was selected and not replaced, what is the probability of a green one? So we want the probability that the second is green, given that the first was green and not replaced. And again, that's very important that we keep that in mind, that that first marble has not been replaced. So now, if I don't replace the marble, not only is my total going down, but the number of green marbles also is reduced from 5 green to now 4 green. So when I calculate my probability of green, there's only 4 greens left to choose from and only 7 total marbles to choose from. So my probability would be 4 out of 7. Let's take a look at another type of problem. Here we have 4 different sets, set E, T, G, and F, which are all subsets of our universal set 1 through 12. If you ever see this notation, D12, this is the author who wrote this. That's their notation for saying a dice with so many sides. So D12 would be a die with 12 sides. And we have 4 subsets, which they've listed out for us, which is nice of them, and they even gave us the probabilities of them. Notice that they didn't reduce these probabilities. That's because when you're doing conditional probabilities, you typically don't want to reduce in the middle of a problem because it could actually help you, and you'll see what I mean when I go to do the calculations. However, please do reduce your final answers in the end. Okay, so in part A, we want to eventually calculate the probability of E given G. But this author actually set us up a little bit to calculate that conditional probability by having us focus on the AND sets and probabilities first. So notice the difference between the first line and the second line because it looks like it's asking the same thing. Set E and set G, and then probability of set E and set G. But the difference is one is actually asking us for the actual set. What outcomes are in the intersection? Whereas the second line is asking us for the probability. It's very important that you see the difference between these because they are 2 different types of problems. So let's talk about the intersection. Where does E and G overlap? Now you could, if you want, trace these out with a pencil lightly and then erase as you go through them. I'm actually going to erase as we go just because I don't want my sets to get too muddy. All right, so set E and G, I'm going to go ahead and just circle anything that's in common to E and G, just comparing them. So just going through, it looks like 1 isn't in common, 2 is, so 2 is shared. 11 is not shared, but 12 is shared with E. So our set for E and G, the overlap, would be elements 2 and 12. So there are 2 shared elements. Since there are 2 shared elements, the probability of E and G would be 2 out of 12. Now, notice that I'm not going to reduce here because I'm actually going to use that in my conditional probability. If you were giving a final answer, we might as well go ahead and reduce it because that is our final answer for the probability. Okay, so now let's go ahead and calculate the conditional probability. Probability of E given G. As I had mentioned, I think of this as the AND over the second letter. So I'm going to find the probability of E and G, conveniently found on the line right above, and divide that by the probability of the second letter, G, which is conveniently listed up above. So the probability of E and G, as I had mentioned, we just did before. Now I did reduce it because that was the final answer for the probability, but I'm going to actually use what I call the raw form, the unreduced form. And there's going to be a reason for that here in a second. So I'm going to use 2 divided by 12. Next, I'm going to find the probability of G. Probability of G is actually given to us above. However, we could have calculated it on our own. There are 4 elements out of 12, so 4 out of 12. Okay, so if we divide these two values, we'll get our conditional probability. But don't reach for your calculator just yet, because if you leave these two probabilities in their raw form, the universal set number should match, so the 12s should match, and therefore would cancel each other when you divide. So what's going to happen is these 12s are going to go away, and you're just going to be left with 2 out of 4. Or this reduces nicely to just 1/2. And that is our final conditional probability. Okay, let's take a look at some more examples using the same sets. So I'm going to go ahead and erase my intersections from my previous problem. And I'm going to start again looking for the intersections of E and T. So what values are shared between E and T? So it looks like 2 is not, 4 is not, 6 is, so let's circle that one. 8 is, 10 is, and 12 is shared. So we have 4 elements here. We have 6, 8, 10, and 12. So go ahead and list that set. The probability of those 4 numbers would be 4 out of 12. This is my raw probability unreduced. However, if I want the final reduced answer, it would be 1/3. Now let's find the conditional probability that they ask for. The probability of T given E would be the probability of T and E, all divided by the probability of the second letter or the given information, in this case, E. We just calculate the probability of T and E. Yes, it's 1/3, but as I had mentioned in the previous problem, we're going to leave it in the unreduced form so that denominator will cancel. And the probability of E will also leave in its unreduced form as 6 out of 12. Now that we have matching denominators within the numerator and denominator, those 12s will once again cancel, leaving us with just 4 out of 6, which then reduces to 2/3. Okay, a couple more problems. Part C, we want to compare F and G. So let's go back to our sets and look at F and G. F and G listed above. It looks like they share 1, 2, and 12. So 1, 2, and 12. And I'll list that as our intersection set, 1, 2, and 12. And our intersection would be 3 out of 12, or reduces to 1/4. The conditional probability of F given G can be calculated by the probability of the and, F and G, all divided by the probability of the second letter or the given information, G in this case. Once again, the author set us up nicely because we've just calculated the probability of F and G right above it. And by the way, if you didn't calculate it right previously, you'd have to do it at that point. And probability of G is also given at the top of the page as 4/12. The 12s, if you leave them in their raw form, would cancel, leaving you with a final probability of 3/4. Last but not least, D, set G and set T. So we go back to the top and we see where G and T intersect, what elements they share. So looking at G and T, it looks like 1, 2, not shared, 11, and 12 are. So we have 11 and 12, 2 elements that are shared within these two sets. So that's our subset for G and T. And our probability for G and T would be the 2 elements that are shared out of the 12 possible elements, giving us a final intersection probability of 1/6. Last but not least, probability of G given T will be calculated by the probability of G and T, the and probability, divided by the probability of the second term, T. Okay, so the and probability, once again, we calculated above. I'm going to leave it in its unreduced form, 2 out of 12, and divide it by the unreduced probability of t, which is also listed above as 8/12. The 12s cancel, and we're left with 2 out of 8, or 1/4. And that's the end.